Hello. All right. So welcome back. Welcome back to the channel. So I'll just open up my whiteboard just in case. Right. So as you have seen in title, we will be learning about word embedding. So uh, it is going to be, I think, a pretty interesting video. Right. So over the last few videos, we have been learning a lot about language modeling. If you have been following sequentially, which most of you would probably not. Or maybe you are watching this video separately, but don't worry. I have been working a lot on making a lot of videos on language modeling particularly. So if you're interested, you go on check out language modeling. But before that, I would highly recommend this video because this video is, I think, probably lays a very good foundation for language modeling. So one of the most important features, important basic thing that you have to learn before learning language modeling and advanced let's say transformers and all that. The most important thing is to learn how to represent words. Right? For example, if before doing all the calculations and all the complex stuff such as building models and all that, uh, you should first know how to represent words so that you could build models that could work on words. So it's going to lay a very basic foundation on what word embeddings are, and then after that we'll be going through these two papers, which are not that big, not that huge, but will give us a very good understanding of language modeling. These papers are actually pretty old. One is I think from 2013, and other is from the date is not mentioned, but other also is, I think glove is pretty new compared to the Word2Vec, but these are pretty old papers. And after this, I think these papers have played a huge role in building powerful language models. They have played their part in the current language modeling upsurge. So we'll be learning about that. So first, let's say lay a basic foundation for you, where the starting point, where to start before reading this paper. So as you know, language modeling is about building models, right? We have some building neural networks, and building neural networks on text data, right? Building models on text data. So sorry for my bad notation, but we'll be using this text data, and we'll be modeling the relations between the words. We'll be modeling the relation between the words, and also some high level features which will not be, which will not directly, we'll just take this model and uh, train this model on huge amounts of data. For example, we have some many amounts of text. Let's say we have text like my name is Joel. Normally in my language model, you just hide this word Joel, and you'll have my name is, and the model make the model predict this word Joel or any other name. So by this, the model will understand the relations and the attention on the similarities between words and other important things the model has to learn in order to understand language. So before doing that, before building models and language, we have to find a way, and we have to find a way to represent these models. Right, we have to find a way to represent this data. And if you remember, if you are you you know computers normally are better at text, and computers only understand numbers, right? Computers only understand numbers. And even the computers that you use currently, when you are typing a key, each let's say letter, when you're typing on a keyboard or track any pad or some mobile phone or something, each letter is represented with the specific numbers, right? Maybe some binary numbers or something. I mean, we could give some number to each word. For example, let's say the number 1 to this word my, and maybe we give number 2 to this, and maybe now we give number 3 to this, and maybe we give number 4 to this, right? We could easily like tokenize these values. This is called tokenization. Just giving one token for each word, and it's maybe in like some one hot manner where we have like zeros, and where we have like n number of values in a vector, and where let's say here in the first example, the first index will be one. In the second example, in the word for the word name, we'll have and I'll just draw him. I'll just draw this for you. Sorry. I'll just draw this for you to make it clear. Zero zero one 000. Right, so we'll have one at the specific indices where what the token actually of the value actually is. I mean, we could definitely represent the words this naively. I mean, this would. I mean, we could have partially solved this problem. We could we have a starting point to run the models. We could run the model with this data. Represent each word with a token and throughout the training data and just give that to the model. We could definitely do this, but the problem here is that in neural networks, the main thing that a neural network does is to able to find patterns in data. And talking about this specific case, each word has no semantic meaning of what it actually means, right? So there is no meaning for the model to find patterns on, right? So there should be some type of relation and some type of nearness and farness between these words such that the model can understand that. So if I have these tokens, so let's say I have a n-dimensional plane, and I'm just drawing this into two dimensional just to make sure you understand, just to make sure that we can represent it for our human eyes. So let's say we have an n-dimensional vector or n-dimensional space, right? Vector space, where we have many vectors, many higher dimensional vectors that we cannot see. So let's say each word has, let's say, 100 by 1 size, so 100 by 1 or something. So this is the 100 dimensional space, even though it is definitely not. But so we're just going to have, so let's say I graph, so let's say I point out each word. So let's say in this naive case, so let's say we just tokenize each word and just make that to be the representation of that word. If we graph it, if we try to visualize it, let's say we have my here and we are, let's say, let's just take some new words. Let's say we have tiger, right? Let's say we have some apple, some lion, some any other thing, right? Let's say laptop. Right. So as we have assigned these representations randomly, so each word is represented randomly currently. As we have represented these words currently, randomly, there is no way for the model to find patterns in this data. So this is the data that the model is going to receive. And this is the data that is the model is going to receive, right, on a very high level. But, and as you can see here, there is no absolute relations, right? Neural networks is something about drawing lines, about finding patterns, right? About finding patterns and drawing lines and all that. But yeah, of course, in higher dimensions, and it means a lot, right? We're going to have like different weights, and each dimension is going to carry the weight. So, so there is no actual distance, and there is no similarities. Right? So let's say we have banana here. So what we want is we want similar words. For example, we want tiger and lion to be as close as possible, right? We want tiger and lion to be as close as possible, just to make sure the model has a very good understanding, or the model could easily create patterns in this data. So therefore, in order to give models some understanding of the data, some understanding of what these words mean, and just to represent these words better, we'll use some techniques called embeddings to make sure the similar words are near as possible, and let's say not very similar words such as tiger and bicycle, probably not very similar. We want these words to be pretty far. So we want to create a representation, and we want to create a representation in which the similar words are closer and dissimilar words are farther. So therefore, we use something called embeddings. So I think this idea was, I think proposed pretty back then, probably 2010 or something. So I'll just go through that, what this idea means. So I'll just provide you a very high, I know a very high notion of what these embeddings mean. And after that, we'll be going to this paper, of course. So let's say we have a sentence. My name is Joel again. Right. So what we could do is, on a very high level, even even if you thought about it, you might get this idea. So what we could do is, you can get the eraser, delete this word. So we already have the sentence. Right. Let's say we have the sentence. My name is Joel. Right. We have the sentence. My name is Joel. We already have the sentence. So what we'll be doing is, we'll be just taking my name is. Right. We'll be taking the first three words, and we'll be passing this, or yeah, well, I think I'll draw a line through a neural network, or a, yeah. So let's say, yeah, I'll just clear it up. So let's say we just have a simple dense layer here, or just some activation sum layer, weighted sum. Right. So each here will have weights, W2, W3. Right. And then we could definitely have like many other things like this, many other layers, or many other layers. Right. I'll just build like this. W1, W21, 22, W23, and we have, of course, we can have like many other things. So what we'll be doing is, we'll be having like weighted sum, right? And then after calculating this weighted, so basically what we are doing here is, we are just, I'm just drawing the notion of a neural network. If I hope you are aware of neural network. I mean, definitely we have many videos in this channel. Check it out when it could help you. So first, I would highly recommend you to learn about neural networks before coming into this one. It is fairly simple. So basically, on a neural network, what we'll be doing is, we'll be just taking. So yeah, of course, before we are not going to pass these direct words. Of course, we are going to have tokens 1, 2, 3. Yeah, we are going to have one hot embedding, a one hot representation. 0, 1, 0, 0, 1. So yeah, we'll be giving this representation. Forgot this. Just forget these words. Just we will be providing these representations, these random representations, to this neural network. So in this neural network, we are going to have weights. We are going to have weights, right? So we are going to have W1 and W2, right? We are going to have, let's say we have, for each word or for each input, we are going to have two layers. We are going to have like two layers of, or like two neurons, right? We're going to have two neurons. This is one neuron, this is one neuron, and each neuron is going to have separate weight for each output, for each input. So for input for input 1, 0, we're going to have one separate weight vector for this first neuron, and we're going to have separate the W21 weight vector for this neuron. So this is actually neuron, and each connection here is going to carry a weight, just like a weighted sum. We're going to have a weight which we are going to multiply with the input, which is not the text, but this vector. So after calculating this, so we're just going to have, first of all, before starting training, as we have running the first step, these weights will be randomly initialized. That's first, before starting training, these weights will be completely random, just completely random numbers. And of course, this weight will have, based on the amount of, based on the input shape, we're going to have a vector or a matrix based on the input shape. And then, we are going to have this weight, right? And we're going to multiply this weight with the specific input vector. We're going to have like two neurons in this case. So what we're going to do is, we could just have a loss function, and we could have a loss function. Just a loss function is nothing but just a function in which we are going to have to calculate something, and the model output is, or the model goal is, to reduce this loss function. So we're going to have, let's say, loss function such as, predicting the next word. Let's say the loss function is predicting the next word. So essentially, the model is going to take these three words, my name is, and the model will be asked to, right, the model will be asked to predict the next word, right? Which is Joel, right? The model should predict the word Joel. And let's say we have another weighted sum. So this is the output layer. Yeah, just you don't need to write weighted sum. So this output should be equal to Joel. And that is what the output should be. Take this previous three words and predict the next word, Joel. And in the loss function, we're going to have, let's say, a difference. We're just going to calculate the difference, or it's a binary cross interval function. So if the output is Joel, so we're going to have multiple classes, right? The model has something called vocabulary, which is the collection of all the words that the model know. So in this vocabulary of all the words that the model know, the model would first predict a word randomly, but as training goes on, the model will hopefully get to this variable. Hopefully it will predict this name Joel. So if the model predict the name Joel, we are going to have some set of weights, right? So so we're going to have a loss function, and we're going to carry out back propagation, which is nothing but the derivative of loss function with respect to each weight. After calculating the derivative of loss function with respect to each weight, we are going to have a bunch of chain rule and all that. So after calculating the derivatives, we are going to update these weights. And as training goes on, the model will try to reduce this loss function as much as possible. And whenever we reach the optimal position, which here in this case, the optimal position is to predict the word Joel. When the model predicts the word Joel, these weights, right, we're going to have a bunch of weights, right? These weights will be stored. So therefore, when we reach the final global optima, we are going to have this word, let's say my. So this word will have the embedding of W1 and W21. As in this notation, you can see that this is W1. So this is W1. Sorry, this is W1, and this is W21, something like that. Yeah. So this is going to be the final embedding of the model of the name y, and we carry out this process for all the sentences, right? We carry out this process for all the sentences, and for repeating sentences, we are going to take this my, and we're going to update it further for different word also. For example, there is another sentence such as my name is, let's say, Karthik or something. So therefore, we'll take this vector as a main position or the initial value, and we're going to update this value for the other sentence also. So therefore, we'll follow this method of updation, right? For each sentence, for each pair, we're going to calculate this thing, and it's actually quite intuitional and quite straightforward. I hope you got the idea of embeddings. We're just going to have some neural network, right? We're going to have a bunch of connections, weighted sums, and then we're going to have each weight, and we're going to have a loss function, which is going to be, yeah. So basically, we're just solving the problem of predicting the next word. And if we are predicting the next word, we are just going to save the weights of the current neurons, and that is going to be the embedding of the model. And by this, the model could understand or change its embedding over time. And as we go on, as we have completed this process for many sentences for a very long time, we could finally get to a point where I'll just draw a diagram for you. So the final position, sorry for my bad handwriting. Hopefully the final position is going to be let's say 100-dimensional vector, whatever dimension, don't care about the dimension. We'll be having we'll be reaching this stage where similar words would be grouped together, right? Let's say apple and banana. Similar words will be closer to each other, apple and banana, or something, and whatever. Yeah, let's say laptop and mobile, and yeah, something like that. So similar words such as tiger and lion that occur together would be closer to each other, because the context in which both of these words occur, in the context in which tiger and lion would occur, would be quite similar, right? So the words that are with tiger would most probably be with the words of lion. So therefore, there would be some type of understanding, and this is not a very good way. This is not a very good way saying that both will be near to each other, but also some type of meaning will be carried out. Some type of relations between these words will be carried out for the model to further train in a separate neural network for language modeling. So that is a basic idea that I want to tell. And now let's go to Word2Vec. I just covered everything very fastly. So just to make sure that we don't have like huge amount of videos. We just reading a bunch of repetitive things. So I think I've already read this paper. I'm just going to share what I know. So let me just go to the whiteboard and just tell you about Word2Vec. Right. So this is the normal embedding that we carried out. So, and then there is something called Word2Vec, in which there is not a huge like difference. I don't think there is a huge difference, but the main difference is that when we have let's say a sentence, my name is Joel again. So rather than deleting the word Joel, rather than doing that, we'll just delete the middle word. Let's say is. Right? There is no middle word here, but we'll just delete the middle word is, and then now we update the parameters, and we'll have a neural network in which we update the parameters for my. So I'll just draw the diagram for you. Sorry, I'll just draw this diagram for you. I'll just have a neural network. Right, we're just going to have an output in which we are going to save all these values. So what we are going to do is another thing that we are going to predict is, so the output of the neural network is going to be this value. Hopefully is, so hopefully it is going to be is. It is going to be is, and then the goal of the model. So we are going to predict is, right? So we're going to have a bunch of weights. So therefore, what we are going to do is we're going to take this is and again pass it to another neural network. So this is Word2Vec. So we're going to pass this to another neural network to predict the other words. We're just going to predict my name and Joel. Right? We're going to take in this is and predict these words, my name and Joel. And this process is actually quite more in depth. Like if you think about it, we have many weights and many tasks the model is doing. So we're going to have two neural networks. Right? One is going to we're essentially like multitasking here. Right? Here in this first case, we are updating these values for the weights, the embeddings of my name and Joel. So it's going to take this my name and Joel, pass that through a neural network and predict the word. And then based on this output, let's say the model, when let's say in the starting position predicts another word. So this word also will be taking this to another neural network. And I think the same neural network maybe, yeah, or maybe other neural network to predict the other words, the surrounding words. So I think this I don't know the name, but I think this is called something called Seabow and something. I forgot the name, but what we are going to do is we're going to follow this architecture in which we are going to first predict the middle value and then use the middle value to predict the surrounding values, just to make sure the weights are just we are like multitasking here, right? So this is, I think, Word2Vec on a very high level. I'll just try. Let's just try to read the paper, just or at least the main part. I think this is the main part. The probabilistic feed-forward neural network language model has been proposed in one. It consists of input projection, hidden layers, hidden output layers. At the input layer, previous words are encoded using one of V encoding, where V is a vocabulary. The input layer is then projected to a projection layer P that has dimensionality n into d using a shared projection matrix. As only n inputs are active at any given time, composition of the projection layer is a relative cheap operation. The NLLM architecture becomes complex for computation between the projection and hidden layers as well. I'll just is However, several practical solutions were proposed for avoiding it. So yeah, I think they're just solving some sorry, memory storage things. So I think I don't know where the main thing is shared. Yeah, so we propose two novel model architectures for computing continuous vector representations of words from very large data set. The quality of these representations is measured in a word similarity task, and the results are compared to the previously best performing techniques based on previous types of neural networks. We observe large improvements in accuracy at much lower computational cost. That is, it takes less than a day to learn high quality word vectors from a 1.6 billion words dataset. Furthermore, we show that these vectors provide state-of-the-art performance on our test set for measuring syntactic and semantic word similarities. All right. Um, Previous word model architectures. Yeah. So the main difference. So I think the main difference between word embeddings and the Word2Vec model is that in word embeddings, so in like normal word embeddings, the one I've shared above, we are just going to predict the next word. So we will only be having the relation between the current word and the next word. Whereas in Word2Vec, we will have some type of contextual ideas. So the model would not only understand the word currently and the next word, or they or not only in one direction, but in different direction. Like so, right? So the model, so each word would have a representation of what it means, and it will also carry the representation. The surrounding words also would have some influence in this words embedding. So that is the main thing here, and I think I'll just stop the video here. I think it is pretty long. So in the next video, we'll be covering this global vectors for word representation, and also I'll also try to cover another paper in word embeddings and maybe go deep into Word2Vec also. So thanks for watching. I'll see you in the next one.